Well, most ideas start off being rather fragile and vulnerable, so you have to protect them a bit before you jettison them. But I think philosophers of science sometimes get a wrong impression, influenced by Thomas Kuhn, who emphasised the idea of science proceeding by normal routes and the occasional revolution. I mean, I think there's only been one or two revolutions in the Kuhnian sense over the whole history of physical science. Most new ideas in science don't overthrow the old ideas. They transcend and generalise them. For instance, Einstein didn't really overthrow Newton. He extended Newton's laws so that they applied more widely for high speeds and for strong gravity, etc. He gives a deeper understanding into why gravity worked the way it did. But he didn't overthrow Newton. Newton is still very viable, and it's the way we do calculations for spacecraft, etc. And I think in almost all the cases I know about, the advances in science have really transcended and subsumed what went before. Very seldom does one really have to wipe the slate completely clean and start again. So science is really an evolutionary procedure, and in most cases, in the subjects I've worked on, it's been led not so much by brilliant ideas, but by new observations, which in turn are made possible by technical advances. And certainly, in my subject, 95% of the credit should go to those who've developed new technologies, allowing new kinds of observations or experiments to be carried out. And that leads to new ideas, new thoughts, new things to interpret, and that, as I mentioned already, is a reason why young people don't have to batter their brains out trying to solve what older guys failed to solve. They can think about new things or use new techniques. So I think that is the nature of ideas, that they evolve and they develop, and one tries to fit some new pieces of the jigsaw to generalise it or complete it, rather than overthrowing everything and starting again. Of course, there are key insights that one has, and the most important developments in science do involve some new idea which is a new unifying idea which links together lots of unrelated thoughts. I mean, Dan Mackenzie was involved in such an idea, continental drift and tectonics, that unified lots of data, and there have been some ideas like that in my subject where you try and piece together some superficially unrelated data into one framework. Of course, the other big contrast between science and the humanities as regards creativity is that although in science your work is durable, it generally loses identity. You add your brick to the corpus of public knowledge, but in general, if you had not been there, then that brick would have been provided by someone else, generally pretty soon. Einstein is perhaps the only 20th century scientist who really made a distinctive imprint, in that had he not existed, some of his ideas might have not emerged for decades and by different routes. But in most cases, individuals play an only marginal role in that what they discovered would have been discovered by someone else. One of the most memorable statements about creativity in science and humanities is in one of Peter Medawar's marvellous essays, where he points out that when Wagner took 10 years off in the middle of the Ring cycle to compose Meistersinger and Tristan, he wasn't concerned that someone would scoop him on Götterdämmerung. Whereas if you are a scientist, if you are Watson and Crick, for instance, and you've taken 10 years off, someone else would have done the double helix. So in science, very rarely does any individual advance the subject by more than a few years compared to what would have happened had they not existed. But that doesn't diminish the satisfaction you get if you feel you have had an idea that has been vindicated.
You said that there were a couple of Kuhnian revolutions. The example Kuhn, of course, concentrates on in his famous essay is Galileo and Copernicus. Is that one of them?
That is one, and I think probably another one is the quantum revolution in the early 20th century, because obviously the concepts of quantum theory were completely counterintuitive and were completely different from the mechanistic view. Of course, we do now realise that they are consistent with it, and it's only when you get down to the micro world that these counterintuitive, spooky elements of quantum theory come in. But I would say that was such a remarkable conceptual innovation that it does count as a Kuhnian moment, as it were. Incidentally, that really leads to one of the other things that I marvel about when I do my own science, which is how far we can get with common sense intuitions. The fact that our brains, which coped to deal with the everyday experience of our ancestors, can go so far in interpreting phenomena far, far beyond the experience of our ancestors. But we should not therefore be surprised that you can't extrapolate indefinitely. When you get down to the world of the quantum, then you can't use the everyday concepts of mechanics, and similarly when you get up to the realm of the entire universe, again ideas of space and time that we've grown up with have the modification. But I think the remarkable thing is not that we have to develop new intuitions for the extremes of the very large and the very small, but that our brains and our intuitions have been so successful in making sense of the physical world.
I had a test for checking the little green men idea. I had to pinch myself actually to really take this seriously, I admit. But I was made to think seriously about this by, I don't know if the name Teddy Bullard means anything to do, the late Sir Edward Bullard, a famous geophysicist. It was a bit frustrating for me in these exciting days, because I had to spend a week closeted in my room in Churchill College marking the scholarship exam. we had an open scholarship exam in those days, I'm sure you'll remember, and these had to be marked quickly and immediately, and that meant the full-time work for about a week marking scholarship papers, and that was almost directly after the first pulse had actually appeared on the records. The first pulse appeared on November the 28th, and the scholarship exam was about the 1st of December, so I was very busy, tied up in Churchill College, and I was having lunch there one day, and sitting next to Teddy Bullard, and I quietly mentioned to him the fact that we were picking up these unusual pulses, and what did he think about it? And he said, well, if they're narrowband, they're probably intelligence. Very wise remark. And so he took it seriously, and I had to take it seriously. And we were, in fact, already measuring the bandwidth, and they were indeed narrowband signals instantaneously. But my argument was that if you have intelligent signals, they're likely to be coming from a planet, and a planet has to be in orbit about a star. So by then, working in my room in the old Cavendish and doing careful timing of these pulses, I'd already discovered that they were keeping time to better than a millionth of a second per day, and I realized that I could detect planetary orbital motion very quickly if they were coming from a planet in orbit about some distant sun, and so I set up measurements to do that. I timed the pulses accurately for, well, I did it in the end for just about a month. But I decided that if I could detect this planetary orbital motion using what we call the Doppler shift, as the planet accelerates towards and away from the Earth, you can detect that by what we call the Doppler shift by careful timing measurements. And I set up timing measurements and carried these out myself for several weeks, and ultimately discovered that the only orbital motion present, there was a huge orbital effect which turned up immediately, but that of course was the Earth itself in orbit about the Sun. That produces a big Doppler shift in the timing of the pulses. Having subtracted that out from the data, there was nothing then left, or if indeed there was orbital motion, it would have to be in an orbit so distant from a star that life as we know it wouldn't have been possible. And that took me, as I said, the first pulse was about November the 28th. I was doing Doppler shift measurements from the first week of December. I think I started about December the 12th, 11th, and I did that right through December until early January. And it took me that time to prove that there wasn't any additional Doppler shift apart from the motion of the Earth. That eased my mind quite a bit, because it's not physics anymore. If it's intelligence, it's a different line altogether. But at the same time, Jocelyn had been analysing past data, because it was likely that if we discovered one, there were others of these sources on the charts. And she came up with 3 others, which eventually she checked, and they turned out to be pulsars too. So it would perhaps be a bit unlikely that you'd suddenly start picking up intelligence from various directions in the sky, intelligent signals, but not necessarily so, because, I mean, if it's there, there are lots of planets around. So anyway, my mind was a little bit easier at that stage, but I had discussed with Martin Ryle before Christmas, when I didn't know the answer, what on earth are we going to do with this data if it turns out that intelligent signals are a likely explanation? And you can't just publish it, and you can't just release it as a news flash. We thought we'd work through the Royal Society in London, actually. We'd inform them and get them to consider it, and perhaps have some national statement about this. But it was too big a thing to be handling on ourselves. And should the evidence have been pointing towards intelligence, we would have then, without making it public, approached the Royal Society and say, here, we've got this, what do you think we should do with it? Luckily that never happened, because by about the first week in January, as I was saying, I had found no Doppler effect for planetary motion, and Jocelyn had come up with 3 others. So we then started to hunt for scientific conventional explanations, and I went to the library and looked up books on midget stars and so on, discovered that white dwarfs and neutron stars were possible solutions, and we had enough to write about without saying what they were, but I mean, just describing the work that had been done was quite a lengthy job, and I wrote a lengthy later letter about all this, and hinted at the end, plausibly, this could have been oscillations of a white dwarf or a neutron star, and we left it there. But of course that was when the balloon went up, and we kept our mouths tightly shut, for which the Americans criticised us roundly later, but I don't repent for a second.
Why
I gave
did
a
they
lecture
criticise
in the old Cavendish, because I felt it was unfair to local people not to hear about it from the horse's mouth, rather than read it in the scientific press. That isn't right, because people knew that something had happened, but they didn't know what it was that had happened. I mean, half a dozen of us knew, and so I gave a seminar in the Cavendish. It was meant to be a group seminar for about 30 people. It turned out to be more like 100, because the grapevine worked, and people like Fred Hoyle were there, and I gave a seminar which let the world know what was going on.
Which room did you give it in? Do you remember?
In the Maxwell Lecture Theatre,
Yeah.
which I knew well from my undergraduate and my early teaching days with it myself. A lovely room to give a lecture in.
Exactly, yes.
So probably the single greatest breakthrough of the last 10 years has been the realization that gravity is describable in a way without using gravity. So as I explained earlier, gravity involves the deformation of space. It's a curving of space, and that's always been our picture since Einstein. But in the late 90s, a young Argentinian physicist called Juan Maltesina made a conjecture which is extremely interesting and exciting, and for which there's now a huge amount of evidence that it's correct. The conjecture was that in certain situations you can take a chunk of space which is dynamical, so the space can warp and bend, and that's gravity. You take this chunk of space, but the space is bounded by essentially a container. I mean, there's a boundary of space. And on that boundary, you have some matter moving and interacting with itself. But the boundary itself is not dynamical, it can't change. There's no gravity on the boundary. It's literally like having, if you like, a rigid cylinder, but with rubber inside. So it's flexible inside, but rigid on the boundary. Now his conjecture was that you could describe everything that happened in the interior purely in terms of what was on the boundary. It's called a holographic principle. Holography, as you know, is when you map a three-dimensional object into a two-dimensional picture. And that was his picture, that the interior would be mapped onto a rigid exterior, and then you could use a description, you formulate a description of the world entirely in terms of what happened on the rigid boundary. And so this is very exciting, and it has been used to understand black holes, for example, when black holes evaporate and release their energy, how that process occurs, and how the information trapped in black holes emerges when they evaporate. But in the last few months, we've been using this to understand cosmology. So what we do is we map a dynamical universe, which is called the bulk. It's the interior, the sort of dynamical part of space-time. We map that onto a boundary, and we follow the system as it goes towards the Big Bang, or Big Crunch. So it heads to a singularity, and then we see what happens on the boundary, in the singularity. What we've shown is that on the boundary, you can describe exactly how the system goes through the singularity. And once you've gone through, so essentially you take the bulk which has gravity in it, you map it onto this rigid boundary, you follow it till it hits the singularity, you follow it through the singularity, you come out on the other side and you map it back into the bulk, where it's again described by gravity. And so we've constructed the first complete model of passage through a singularity. And it's very fascinating. Not only, it appears, can the world go through a singularity and survive, which is again, and this is another picture of the brain collision, in fact. The two things are related. So not only can that happen, but also in the process of heading towards the singularity, it turns out that variations in the density of the stuff on the boundary are created. And these variations in density from place to place are of exactly the form we need to explain the variations in density in the real universe. They're called scale invariant. And so the variations we see, which gave rise to galaxies, are known as scale invariant, meaning they're the same on all scales. And scale invariance is a very simple property. It's also a reflection of an underlying symmetry. And what happened is that Maldaceno's picture, whereby gravity maps to matter in the bulk, on the boundary, that picture, the boundary theory, is automatically scale invariant. And so that scale invariance of the theory translates into the scale invariance of the density variations. So we've written a couple of papers about this, and there are many aspects still to be completed in the picture, but we think we have the means to do that. And if this is correct, if this picture turns out to be correct, it will be easily the most elegant explanation of the origin of the density variations, because it really all comes from symmetry principles, from gravity and from symmetry principles. So this is very exciting, and I'm presenting this work at several talks in the near future, and we'll see what the response is.
You then went on, I mean, you've had a whole new set of work, and could you explain this work, which you've alluded to a lot of time, which is zinc finger work?
Well, yes, it's in my introduction. Did I give you this?
Yes.
This thing tells the story. This is I was asked to write yes. Well, it says how I came to do it. I became interested in active chromatin. That's chromatin which has already been, the DNA has already worked itself loose, or it's being worked loose in some way from the chromatin. It's about to be transcribed. That is, the regulatory proteins which are going to switch on the gene can get access to it. And that you can show, this active chromatin, because it's now become susceptible to enzymes, DNA enzymes, which will attack the DNA. So you found, if you looked at chromatin, which you extracted from living cells, you'd find that some of the chromatin was accessible to enzymes, and those correlated with, once you knew what they were, these would be genes which were going to be activated. So I began looking for a source of active chromatin, and now and I wanted to investigate that. It's described in the introduction here. So I read a lot of the literature. Now, if I was going to do structural work, that's X-ray crystallography, biochemistry, and possibly electron microscopy or things of that sort. If you're going to do that, you need large quantities. So I looked for something which you get milligram quantities out. So you can do a lot of biochemistry using microgram quantities. This is because the proteins are run on polyacrylamide gels. We only have very trace of proteins, and these show up in what's called gels at exphoresis. So I wanted something that you could get quantities on to crystallize or to investigate by serious biochemistry. And so I found that there was reading literature, there was a gene of in Xenopus, the South African frog or toad, which was present in large amounts. I was alerted to it by reading various papers, and one of my colleagues, Hugh Pelham, had actually worked on it, my current colleagues, and he showed me some, and I see if we get large quantities through it, so I decided to work on the 5S RNA genes of Xenopus. These make 5S RNA, which is the product of the gene. In this case, the 5S RNA gets incorporated into ribosomes, which are protein synthesis factories. That's by the way. And so I decided to try to get to work on it. And I had a new postdoc, a young man called Miller. I put him to work on it, and I discovered, or uncovered, by a series of purely biochemical experiments over a period of several years, that this had a repeating structure. There was a repeating structure in the. There was a repeating structure in the, and this was the repeating structure, and it had 9 units. And this is the DNA, and these 9 units bound to the DNA. And so what we knew at the time is that they had certain cysteines and histidine residues, C's and H's here. So I interpreted this as folding up into little units, and each unit bound a certain number of bases. And when the sequence came out, the protein sequence, the amino acid sequence came out of the zinc fingers, here you are, 9 of these repeating units, and these are the 1-letter code for amino acids. And you see they have 2 cysteines and 2 histidines in each of the units. And these are the ligands. These are the commonest amino acid which bind zinc. And we measure the amount of zinc, and there was between 7 and 11, and there are 9 of these. So it was all done biochemically. Later on, people thought it was all done by bioinformatics. It's a load of cosmology. It was all done by chemistry, but people couldn't grasp it. Still people are writing it was all done by bioinformatics. So it went on from strength to strength, and this is the most common. It's the most common motif. And here you are. The total number of genes. 3% of the human genome consists of cysteine, 2 histidine, 2 times zinc fingers. There's another type of zinc finger called C4, which I won't go into now. And you see, as you go up in the evolutionary scale, you get more and more of these. So down in the C. elegans and the worm, and the zebrafish, you get 1.7%. In the human, you get 3%. So you see, they're a marvelous modular system. It's a combinatorial system. You can combine the fingers. Each finger has a different amino acid sequence which can recognize the sequence of DNA. And so this became a tool for, so it became the ideal tool for making artificial synthetic fingers for having access to genes. This has become a big technology. Did I send you any of the press releases?
You sent me one, yes.
Yeah, well, that was the. So now it's in patience, and so it's a really major. Well, it's a major piece of work, and it's taken some years to. I started out doing it myself, but we formed my colleague Yan Chu, who was half Chinese and half Greek, very entrepreneurial. He left the lab. He could have stayed on here to form a company called GenDAC. Have I mentioned this before? GenDAC, Gen for gene, DAC for dactyl, Greek finger. And he founded a company and got some backing from it. And because the MRC, we took out patents, I should say, because we took out patents, and the MRC held the patents. And in the lab, we started making libraries of zinc fingers. We began to work out the rules of recognition. And this GenDAC was bought out by an astute American who created a business. Yan Chu created a research establishment, very high class, very high powered, but no money, because people didn't invest in it. There were a few backers from an MRC seed fund, and so Sangamo, which means Sangamo doesn't mean anything. It's named after Sangamon County in Illinois. His grandfather had a business there, and and so I go to the States 2 or 3 times a year, and they now going great, as they would say. They might even make some money. It's now it's become the method of choice of. It's also now in plant agriculture, and it's going to make the old-fashioned GMOs look like steam engines compared with the internal combustion engine. And it's being developed by Dow Agricultural Sciences, and the American company, and they say this is game-changing technology. That's high praise indeed.
Paradigm shift, indeed.
Paradigm shift, yeah, game-changing.
The problem with speaking to camera this afternoon is that maybe next year the answer will be completely different. It just kept
That's right, it's dated.
It's dated. And the current big push is with Plastic Logic, which I had a role in founding in 2000. And Plastic Logic has found we have a very, very good technology for being able to put down huge numbers of surprisingly good transistors, which are made out of plastic, onto a sheet of plastic. And those we're using to switch a display, an electronic paper-like display, which is also flexible. So we end up with a display that feels like a sort of laminated card. At the moment the active area is A5 size. It's quite substantial, about 1.5 million transistors in it.
Gosh.
And that, I think, is going to be what everyone has always wanted, to be able to read, say, on the bus or on a train.
The quality is the quality of.
The quality is, it feels like reading black on white. It has the weight of a lightweight book. You can bend it.
You don't turn over the pages.
So you just press a button and the page will change. So I'm not sure what format will be finally used, but we are spending lots of other people's money building a manufacturing plant in Germany to manufacture these, and by this time next year we'll know whether it's hit the market successfully or not. But that could be big. There are with Cambridge Display Technology and the light emitting diodes, it's been hard, but we now have astonishingly good full colour displays. They're not flexible yet. There are practical reasons for that, but they
they're better than liquid crystal displays for TV, and that company has ended up being Japanese owned. A lot of that part of the display industry is necessarily going to stay in Asia, but I believe that technology will find its way into top performing displays.
For computers?
For computers, mobile phones, where performance is absolutely at a premium. And then the big area which may turn out to be very important is making low-cost solar cells, where silicon is fundamentally too expensive. What one, I think, needs is a technology which is cheap to make, cheap to deploy, maybe doesn't last forever, but by the time it's worn out, it has many times over paid for itself in terms of carbon dioxide not generated.
When you say solar cells, I know nothing. Are these things that capture sunlight
and produce electricity?
I remember reading an astonishing fact, which was that if you could get, an effective system that would capture even a small proportion of the sun's energy and cover, quite a small area of, at that time it was said the Sahara Desert, which is not perhaps where you put it, but you could produce an enormous amount of energy.
Sunlight is essentially the only truly unlimited energy resource we have. You could meet the entire energy requirements of the USA today by coating the state of Kansas with not particularly efficient solar cells.
It would have to be over the whole surface.
Over the whole surface, but Kansas is a small fraction of the USA. That's all it would take.
And that would, I missed the crucial bit, that would be enough for the USA?
Well, the USA accounts for a quarter of world energy consumption at the moment, and that would be the whole of the USA. So if you could look at maps of the world with 4 such areas dotted
Australia.
Australia, Saudi Arabia, the Sahara, and that's world energy consumption. So
is this going to be possible?
Things are possible. There are sort of reality checks, and at the moment solar cells which are made out of silicon, and it's a very expensive technology. It requires a lot of energy to make them. And I haven't done the calculation myself, it's very hard to check, but I'm assured that if I were to put a solar panel on my roof and leave it switched on all the time, so that every coulomb of electricity that came out of that solar cell avoided some fossil fuel generated electricity, it would take 5 years before it had paid back the carbon used to make it and put it on the roof. Which is a depressing thought.
You were going to say that. Yes.
So you've got to bring that sort of payback time down.
But what you were saying earlier is that you're developing an alternative to silicon.
We may be able to do it. We have. I mean, they're not good enough at the moment, but there's a significant chance that this is a route to a low enough cost, larger